All right, let's talk about time dilation. Now, when something starts to move at a significant fraction of the speed of light, the way that time is perceived by the different people starts to change. Um, when this person looks at their clock, they see it moving at a normal rate. But when this person looks up at this person's clock, they see it moving very slowly. And when this person looks at their clock, they see it looking normal. But when this person looks at this clock down here, they see it moving very fast. And you might want to pause this and go back and listen to that again, but both people see their own clock as normal, and they see the other person's clock as behaving differently. But that's why we're talking about how it's perceived is going to change. Let's take a look at Y very briefly, the math here. Found a pretty nice proof online. I've put it here. So I've got a light clock, two mirrors, and a beam of light that goes down, hits, and goes back up. A tick is when it goes from here down and back up. That's one tick. So if I'm in this frame of reference looking at this light clock, the light would go down, hit, and go back up. Yes? So we're measuring, for us, we're measuring what we would call proper time because I'm in the frame of reference of this clock right now. And if we say that the mirrors are a distance d apart and the light has a velocity of c, yes, the time velocity is distance over time. The distance in this case happens to be distance over time, sorry. The distance happens to be 2d because it goes down and comes back up. The velocity is c. Time, I solve for time, I get 2d over c. Yes, and we call this the proper time because it's your time. It's proper. It's the time of the frame of reference that you are in. Easy. However, now I'm in a different frame of reference to the light clock. The clock is moving with a velocity, in this case we say u, in this direction. Now if everything was dark and I was looking at this light clock from up above and I could only see the light, that's why I'm saying it's dark, I would see the light travel in a path like this. Yeah? And the time it takes would now be different. And I hope you realize that down and then up is shorter than this and this. Yes? This is D. This is going to be longer than D. So things are about to change. So we use Pythagorean theorem. And again, if you're not interested in this proof, don't get stressed about it. But I use Pythagorean theorem to find L here. It's this, and how fast it's moving in this direction would be this is a distance, yes, and it's equal to VT in a way, the simple formula, and that's U T, and it's a half of that because I'm only going from here to here. So that's where they're getting this term from. And from up above, I see this. It's just rewriting that equation. Yes, we combine the two equations. We do some rearranging. Yes, and you can pause this and read and follow through. I do some simplification and some solving, and it's really, it looks like crazy. It's really not that bad. Don't stress about it. But I do some collecting of like terms. I do some factoring. I do some rearranging, and I actually get this nice formula right here that has a relationship between the time in one frame of reference, the time in another frame of reference, to the velocity that you're traveling. So in our text, if you happen to have our textbook, and I will be putting a couple of pictures of our textbook in the document. In our text, it uses, instead of T and T0, it uses TM and TS. So TM is the time interval measured by an observer who sees the clock moving relative to themselves. So TM is the frame of reference that has the clock in it. And TS is the time interval for an observer who is stationary with respect to this moving clock. So this is the moving one, and this is the stationary one where the people are looking up at it. Note here, V squared can never be bigger than C squared, so this is always less than 1. 1 minus something, I'm always going to get this square root is less than 1. And if this is less than 1, something divided by something smaller than 1 is going to get bigger. Tm is always greater than Ts. Now you might say to yourself, this is all hogwash. Is there proof? Yes, one thing that we use GPS, and all GPS satellites use relativity in their calculations. It starts to get, we get a large amount of error involved if we didn't use it. With relativity, the error gets down to like plus or minus 10 meters, which is pretty good. They actually did an experiment with planes. Yes, they took 2 atomic clocks, yes, which are incredibly accurate clocks. They put one on the ground, and they put one on a plane, and they flew the plane around and around and around and around and around and around and around, and then afterwards they put the 2 clocks side by side, and the one that was flying was different than the one that was standing still. Not by a lot, but you needed an atomic clock to actually show this very minute difference, because the plane is not traveling at any sort of significant fraction of the speed of light. So they had to do it, I think they did it for like a month, and still the difference in these 2 clocks was extremely small, but they were definitely not the same. So let's do a question, a sample question. So I've got a beam of particles, travels at a speed of 2 times 10 to the 8 meters per second. Their average lifetime is, and that's Tm, because that's this is their lifetime in their frame of reference. Yes. What would be their lifetime if they were at rest? And at rest, this one. So I get C is we'll use 3 times 10 to the 8 meters per second. Yeah, I'm not putting times 10 to the 8 on the top here or on the bottom, because they'll just cancel out. And if I solve this, I would get 1.2 times 10 to the minus 9 seconds. So they definitely last longer if they are moving. Another thing about time is twin paradox. If I have 2 twins and one stays on Earth and the other one gets in a spaceship and goes for a ride. If this one is traveling at a significant fraction of the speed of light, when it returns to Earth, time for this person would be smaller, time passed, than this person. They would literally be different ages upon their return. And we can try this question here. Two twins, 30th birthday, one twin goes on a space journey. Here we'll put the velocity is I'm in trouble with my pen. Oh, there it is 0.99 c, means it's 0.99 times 3 times 10 to the 8 meters per second. Wait a second, what's the notation here? TS. That's how long this person thinks, the person on the plane or the rocket thinks it lasts 1 year. How long does the person on Earth think that it is? And I get TM equals TS squared. When I plug this into my calculator, I get 7 years. So the one on the traveler would be 31 years old, because they left when they were 30, went away for a year. The one on Earth would be 37 years old. And that means that they would now be 6 years apart in age, which is just incredible. Not an easy topic. It's not logical. You're gonna find it difficult to wrap your head around it because it is not something that we come across in everyday life. But I wish you luck as we attempt to try and solve some questions together.